Hello everyone, and welcome back to the next engineering framework. If you're here, it's because you saw our 2028 launch window analysis. If you haven't seen it, I strongly recommend you stop this video right now and go to the link I've left in the description. It's fundamental to understanding what we're going to discuss today. But for those of you who are already up to speed, let's do a recap. An honest and brutal summary of what happened in our 2028 window simulation. It was a bittersweet mission. Technically, it was an aerodynamic triumph. All three Starship B3 vehicles successfully landed. The thermal tile system, the crunch wrap, and the belly flop maneuver performed flawlessly in the Martian atmosphere. SpaceX proved it could deliver hundreds of tons to the surface without crashing. However, once on the ground, the harsh reality of engineering hit us hard. The surface mission was largely an operational failure. The Optimus robots, in their first Martian iteration, couldn't withstand the environment. They suffered severe overheating issues in their actuators, and electrostatic dust destroyed their rotary joints within weeks. They failed to deploy the solar panels on time. To make matters worse, the ISRU life support pilot plant, our canary in the coal mine, stopped transmitting telemetry after 2 months. The filters became saturated, and the reactor chemistry failed. Our canary in the coal mine stopped transmitting telemetry after 2 months. The filters became saturated and the reactor chemistry failed. But this is where the story takes a fascinating turn. The fact that all three ships landed intact changed space geopolitics overnight. NASA, which had been observing from the sidelines with skepticism, saw the intact stainless steel hulls on the plains of Mars and decided to go all in. They realized that SpaceX had the transportation, but lacked the fine materials science and robust nuclear-grade instrumentation. So, welcome to the 2030 launch window. This is no longer a solo SpaceX mission. It's a massive collaboration where NASA brings its expertise in critical systems and scale. The scale has multiplied tenfold in this window. We're not sending 3 ships, we're sending a fleet of 10 Starships in cargo configuration. The goal is no longer validation. The goal is construction. We are going to lay the industrial foundations for human arrival. Let's break down the fleet departing for Mars in these critical months of 2030. First, we have one ship with a completely redesigned version of the ISRU demonstration plant. Second, and this is the monstrous part, 4 ships dedicated exclusively to building an industrial-scale propellant plant. Third, 3 ships loaded to the brim with solar farms. And finally, 2 supply ships carrying spare parts and, most importantly, the first complete pressurized habitats and a version of Starlink optimized for Mars. Let's analyze the engineering behind this titanic infrastructure. Starting with what failed last time: communication and control. Thank you very much, Carlos. I'll continue with the next point: the communications revolution, the end of radio. In 2028, we struggled to control the robots due to bandwidth limitations. Trying to manage an industrial fleet with conventional radio waves is like trying to download a 4K movie with a 90s modem. Radio waves scatter, and at Mars's distance, the signal is weak and slow. By 2030, we've implemented a total paradigm shift: deep space optical communications, or DSO. We are abandoning radio frequency in favor of lasers. The physics are simple yet powerful. By using lasers in the near-infrared spectrum, specifically at 1550 nanometers, we dramatically reduce light beam divergence. Imagine a water hose. If you use a wide nozzle, the water scatters within a few meters. That's radio. If you use a fine pressure nozzle, the jet travels extremely far without spreading out. That's the laser. This allows us to concentrate much more energy on the receiver. Thanks to previous missions like the Psyche probe, this technology has matured. But the challenge is pointing. Mars is so far away that light takes up to 22 minutes to arrive. You can't aim where you see Earth, because by the time the laser arrives, Earth will have moved thousands of kilometers. The spacecraft must aim at an empty point in space where Earth will be in the future. This requires microradian precision, just to give you an idea. It's like hitting a €1 coin from kilometers away while moving. To solve this, and avoid reliance on surface-based aiming, the 2030 Starships deploy an orbital constellation called Starlink upon arrival. These satellites act as repeaters. Ground-based machines communicate with the satellite directly above them, And the satellite uses its high-power lasers and 22-centimeter telescopes to beam the data to Earth. On Earth, we no longer use conventional parabolic antennas for this. We use telescopes equipped with single-photon superconducting nanowire detectors. These sensors are cooled to temperatures near absolute zero. They are so sensitive that if a single laser light photon strikes the nanowire, it breaks its superconductivity and generates an electrical pulse. We detect every particle of light arriving from Mars. The result is a bandwidth of over 1 gigabyte per second. This allows for real-time telemetry of all industrial machinery and high-definition video to monitor construction operations. It's the birth of the interplanetary internet. I'll pause here to mention that on our channel, we have a complete course on these topics. I'll leave the link in the description. If you'd like me to elaborate, please indicate so in the comments. I've worked on this type of technology, and we can provide more information. I know Carlos will tell you more. We ask you to subscribe to the channel. That's the best way to support us in creating more content. Thank you. Thank you, Anna. I'll continue with the next point. Robotics 2.0, semantic classification and swarms. With the communication problem solved, we return to the ground. Do you remember the Optimus robots that failed in 2028? The problem wasn't just the heat. It was that they were dumb when it came to the Martian terrain. They'd get stuck in sand traps that looked like solid ground by 2030. The offloading fleet uses a new generation of robotics with Optimus 2.0 and construction rovers. Based on semantic terrain classification, we use an architecture called soil property and object classification. Originally developed by JPL, we've moved from simple geometric obstacle detection, that is, there's a tall rock, don't go there, to material understanding. The new rovers and improved Optimus units use onboard convolutional neural networks. They don't need to ask Earth. Their cameras analyze the soil's texture and albedo, classifying each pixel. This is safe bedrock. This is compacted regolith. And this is a treacherous sand dune. But we've gone further. We've implemented proprioception. The robots now feel the ground. If the wheels start to slip more than expected, the system automatically relabels that visual texture as dangerous, instantly updating its internal model. They learn as they drive. This is vital because we have to unload 10 ships. We can't micromanage every robot. They operate as a swarm with decentralized autonomy. They coordinate with each other to extract solar panels and pipes from the Starship's cargo bays, moving at speeds of kilometers per hour, not meters per hour like the old Curiosity. They are construction workers, not lab scientists. Thank you. I'll continue with the section titled The Industrial Heart, ISRU, and Propellant Production. Now, let's talk about the most important cargo of this window, the 4 propellant plant ships. The goal is to produce liquid methane and liquid oxygen so that the ships can return someday, and to have reserves for future crews. The chemical process is Sabatier, a well-known reaction. We take CO2 from the atmosphere, mix it with hydrogen, and get methane and water. But the engineering at this scale is brutal. The first challenge is water. In 2028, we failed to extract it reliably. This time, we're bringing the red water system to industrial scale. Forget excavators. We use thermal mining. A drill penetrates the ground until it finds ice. Once there, we deploy a heated head that melts the ice in situ, creating an underground cavity or bulb of liquid water, which we then pump to the surface. It's like sipping a pomegranate through a hot straw. But there's a thermodynamic problem. Mars is almost a vacuum. If you melt the ice and the pressure isn't right, the water won't turn liquid. It sublimates directly into vapor and is lost. The well must be artificially pressurized. Once we have the water, we electrolyze it to extract hydrogen and oxygen. The hydrogen goes to the Sabatier reactor. It combines with atmospheric CO2 to create methane. And here's the bottleneck nobody tells you about. The ratio for Starship's Raptor engines is 3.6 parts oxygen for every part methane. But the natural chemical reaction produces a much lower oxygen ratio. We have a massive oxygen deficit. That's why the 2030 plants have to dedicate an enormous amount of energy just to electrolyze extra water to get that missing oxygen. And then there's storage. We have to keep hundreds of tons of oxygen at minus 183 degrees Celsius and methane at minus 161 degrees Celsius. At minus 161 degrees Celsius. In 2028, passive insulation wasn't enough. Now we're bringing in reverse Brayton cycle cryocoolers. These are high-power industrial refrigerators. They circulate neon or helium gas through the tank walls to intercept heat before the fuel boils off. This consumes megawatts of energy, hence the need for the 3 solar farm ships. We deploy acres of flexible panels and possibly compact fission reactors, if regulations have allowed it, by 2030. To power these refrigerators day and night, because if the power cuts out, the fuel is lost and the mission fails. We come to the last point. Class 1 habitats, the home for humans. Finally, let's talk about the 2 supply ships. They carry something very special, the first real human habitat in 2028. We tested the life support systems inside the Starship. Now we're going to deploy a standalone structure for this first base. We've ruled out inflatable habitats, even though they're popular in artistic renderings. For the fundamental 2030 mission, reliability is the priority. We're going to use a Class 1 habitat, a pre-integrated rigid module, similar to those on the International Space Station, but designed for the surface. It's a monolithic cylinder, 8 meters in diameter, optimized to travel in the Starship's cargo bay. We call it auto-deploy because, although rigid, it has to deploy itself. An internal Starship crane lowers it to the ground. Once there, the habitat deploys telescopic legs with automatic leveling to settle on the uneven terrain. But its most innovative feature is its skin. The biggest enemy on Mars is radiation, galactic cosmic rays. Traditional aluminum is bad for this because when a cosmic ray hits aluminum, it generates an even worse shower of secondary radiation. The solution for 2030 is hydrogenated boron nitrite nanotubes, BNNTs. This is the wonder material. It's structurally strong, withstands temperatures of 900 degrees. But the most important thing is its atomic composition. It has a lot of hydrogen and a lot of boron-10. Hydrogen slows down fast particles, and boron-10 has an exceptional ability to capture neutrons, which are one of the most dangerous forms of radiation, without emitting secondary gamma rays. It's smart shielding at an atomic level. This habitat will be installed, connected to the power grid and pressurized, silently awaiting the rovers. They will cover part of its structure with Martian regolith to provide an extra layer of protection. It will be a beacon of safety awaiting its inhabitants. Thank you, I conclude. The 2030 window is the leap from faith to industrial engineering. We're moving from testing if we can land to building a chemical refinery, a telecommunications company, and a high-security hotel on another planet. All of this operated by robots with advanced artificial intelligence. If this mission succeeds, if we manage to fill, even partially, the tanks of a Starship with Martian fuel, and if the habitat maintains stable pressure and temperature, then there will be no more excuses. The technology will be validated. The infrastructure will be ready. And that leads us to the inevitable question. If we land in 2028 and build in 2030, what happens in the next window? The October 2032 window is the date marked in red on the calendar of human history. It's the window where, if all of this works, we will send the first crew. Do you want to know what the journey of those first humans will be like? How will they survive the 6-month journey? And what will they do when they step into that habitat we just described? If you want us to analyze the third window, that of humanity's arrival, leave it in the comments. Write, "We want the 2032 window." I am a firm believer that the future is built with boldness and technical precision. Thank you for joining me on this engineering journey. See you in the future.